Okay, so hello everybody. I'm Christian and this is Miro. We are from Typefox.io. I think some of you met us already, maybe got some tattoos. I hope you can see and recognize the slides. I just made these stories a bit downward. I hope you won't fall asleep. We both will tell you about debugging DSLs and our new Xtext new tracing API. And first of all, let me clarify what we mean with debugging DSLs. Debugging DSLs does not mean debugging your concrete DSL tool implementation, your parsers and scoping stuff and whatever, but debugging the programs that you have written in your DSLs. Let me first illustrate why this is helpful. Sorry for this flickering. But this is helpful, and to that end, I prepared a little example. I use a very simple scripting language, scripting DSL, which is built based on Xbase in that case. Who of you is familiar with Xbase or have used it, heard it? Okay, so most of you, I don't tell anything new. What this simple program here does is it just declares a list of numbers from 2 up to 100. It copies and filters this list, it performs a fold operation. It joins some elements, prints a result, and finally prints a completion statement, which is done. So, but we have in our execution of the program, there is no result printed. So the result is empty. We just got this completion statement. So, and if we are not able to debug this program within the IDE, what should we have, or what could we do? Since this program compiles to Java, we need to go to the generated code, to the generated Java code, rearrange it somehow in our IDE. It blows up quite a lot. It is quite lengthy, so we need to find our way in this code, make it somehow comfortable. See lots of helper variables, lots of lengthy implementations of closures in here and so on and so forth. So, and while flying over this, we finally come over a variable which is called saved here, and which we recognize we have used it in our DSL program as well, like here. So what we could do is just let us try set a breakpoint at the subsequent return statement and execute our program and see what happens. So, okay, we have reached the breakpoint, so let's put or inspect a certain variable, which is a list of odd numbers starting at 3. And when we continue debugging our program, continue executing it, well, we will see numbers get removed one by one. The list decreases. And so we could maybe see something. But coming back to our original problem, wouldn't it be nice if we could instruct the IDE to allow us the same thing in the DSL editor? Like we try right now, we just say, okay, don't take the Java code, but take our Xbase-based language here and allow us putting breakpoints in there. And as you can see, and as you may know, for Xbase, this works. It's quite a while, but it does not do so generally for general Xtext-based languages. So, and how we could achieve this for those languages too, this is what this talk is about. So let me point this out a little bit. What if we would, or what's required for debugging in DSL? So the fundamental thing is we need to inform the IDE of which part in our program, the wrong way, which part of our program, like this statement or this one, maps to which of the parts in the generated code. So how is the relation between the source code in the DSL and the target code that is generated? And fortunately, Lots of infrastructure for that is already available in Xtext, and it is used by Xbase already. So there is stuff already available. There's actually just a little part is missing. What is also available is Xtext already does part of this job, because Xtext keeps already a mapping of the AST elements that are created by the parser and the code regions in the source code. So again, help our program here and let this graph denote just an excerpt, a simplified version of the AST. Xtext already maintains these relations between the strings in the source and the corresponding nodes in the AST. And for those who followed the talk before of Sebastian and Holger, this is available via these node model utils, and these relations are part of the node model. But in order to compute these mappings from the source to the generated target, there is one thing missing, actually. And this is a mapping of the AST elements to the code that is produced by our code generator. So, and again, let this denote the AST or excerpt. What we somehow need to tell the tool is, which code regions like those correspond to which of the elements in our AST. And it's important to note these code regions are not just a serial line of regions, but they can be nested, like we see here. So let's formulate some requirements on that. We have seen that there is already infrastructure, but what's missing is an API for capturing this information, for capturing these relations in here. And this API should ideally nicely integrate with the template expressions that are offered by Xtend. I'll show you in a minute for those who are not familiar with them. And what we want to do is we need to trace the code regions that is created by the code generator per eObject, or at least per relevant eObject. And eObjects may have attributes, so we would like to distinguish also the code regions that are created based on an attribute of a certain eObject, names, types, information, parameter lists, whatever. Well, parameter list may be a stupid Beispiel, like a stupid example. And also eObjects may have child eObjects, and we would like to also distinguish them within the parent eObjects code region. So, and as I said, let's make a little excursion to Xtend. Xtend was already mentioned also in the talk before, but here I focus on something different. I focus on the template expressions. These template expressions are very, very nicely suited for generating code. They start with these triple quotes, and then you can just write down the code that is produced or that is dumped into the generated files or strings or whatever. You can refer to parameter values, you can call functions, and so on. You can have conditional parts that are just added to the output if certain guard is true, and you can iterate over lists and do per list element, add per list element something into the generated code. What's also nice is are things like the extension methods here, and this is a method that is declared somewhere else, and Xtend allows to prefix the first parameter like we did it here. And what is also very convenient in Xtend is not used here, but will be used by our tracing API that is shown by Miro in a second, are reactive annotations. And one thing I just missed is the most cool thing about Xtend's template expressions ever. It distinguishes white space like we see here and here and here that does not go into the generated code, and white space that goes into the generated code, which is like this one or like this one. So this allows you offers you nicely or allows you to nicely format your templates, but get also nicely formatted generated code. And this is a really cool thing. So with these backgrounds in mind, I will hand over to Miro, and he will explain you the new tracing API and give you examples.
Yeah, thanks, Christian. I would like to dive into the new API for tracing source code to target code, and I will do this using an example which is available here on this GitHub repository. We will show the URL again at the end of our talk. So let's have a quick look at the example language. So this is an example DSL code. It describes classes with properties and operations, and so here we have very quickly the grammar corresponding to this DSL. So classes have names and members. Members can be properties or operations. Properties have names and a type. Operations have name, parameter, list, type, and an implementing expression. So and now let's say we already have this DSL, and we even already have a code generator for this DSL. This probably is a situation where many of you are in. So you are already generating code for DSLs, and we want to now enhance the code generator so that it adds the tracing information. So this is might be very familiar to all of those who have already used the Xtext generator API. So basically you implement this doGenerate method and you get a file system access, which is kind of a layer which you can use to generate files, and either directly in the file system or in memory or in whatever context you're applying this. And here we say this is the name of the generated file, and this is the content declared with the template expression as explained by Christian. So the first very easy step to add tracing information for this whole file content, and let's say we want to trace this to the root object of our model. In that case, we simply replace this generate file call with generate traced file, which is an extension method, which you can see by its red highlighting now. So this is provided by the new API, and you add the AST model element to which you want to trace the content. So this is a good start. So this is very coarse, of course. So it defines the whole file content is mapped to this source model. So now let's dive a bit deeper and have a look at this generate header function, which is called here. This is again defined by a template expression. So it means this is the text that is generated for this parameter class declaration here. And so in order to enhance such a method with tracing information, the new API offers an active annotation called traced. If you add this one to this method, it will make sure that the source element class declaration of type class declaration given here will be mapped to exactly this text of the output. So now let's go even more, a little bit more fine-grained, and if we have a look here, the name of the class declaration is written into this part of the output. And let's say we want to have a mapping between the name property of our class declaration and exactly this part of the generated text. This is also very easy. Just replace this declaration.name by ._name. This is also an extension method that is provided by the new API, and it makes sure that exactly this is achieved. So the output text will be mapped to this name property. Now I want to explain a little bit more where this comes from, because this _name is actually generated automatically specifically for your DSL. And this is done using the meta model of your DSL. So let's get back to the grammar definition. of the class declarations. So we see we have names and members as properties. Xtext using EMF generates a class declaration EMF class from this with exactly these properties, name and members. And it also generates a factory that can be used to generate instances of that. So now all you have to do to get these traced property extension methods is you write a new class, let's call it myDSL trace extensions, add an annotation called traced accessors to it, and you feed the factory class of your meta model as a parameter to that annotation. And this is an active annotation that will inspect this factory through Java reflection and will generate extension methods for all of the properties of your meta model, like, for example, _name for a given class declaration. And this is exactly what we have used in our example of the previous slide. In order to include that in your code generator, you just have to write inject extension myDSL trace extensions. So this is our class that we have written here. Add inject is the Google inject code that makes sure this class is loaded at creation time of your code generator. And this extension keyword makes sure that you can use this _name method as an extension method, so, with a nice syntax. So maybe you may have noticed that the return value of this _name method is not a string or a character sequence or anything like that, but it's a generator node. I want to explain this next. This generator node is part of what we call the generator tree, which is a data structure, a tree-like data structure that has two purposes. So the obvious purpose is to generate the output text for that. So the data structure has inner nodes, which are composite nodes, and it has leaf nodes, which contain the actual text in order. So it's an ordered tree. So now, in order to get the first purpose done, we just need to traverse this data structure and we get the output text. So in this example, we collect all the leaves and then as a result, we get this line of C code as an output. Now the second purpose is to collect the tracing information for exactly this output text. So, and this is done using special inner nodes, which contain the source locations for the output text that are generated by their child nodes. So some of these inner nodes have links to source locations. So and these are just text regions of your source files, which are derived from the AST elements or from certain properties of your AST elements, depending on how exactly you have invoked the tracing. So usually you don't have to worry so much about this data structure, because in the examples we have seen before, using the extend template expressions, all this is done in the background. So the new API generates this for you and makes sure that the correct output text is created and the correct trace locations are created. But there are certain cases where it's very useful to generate parts of the tree directly, and there is some nice API for that too. And the most common example for that is if you want to implement a compiler for an expression language or statements or anything like that, where you have very fine-grained pieces of code that need to be put together. And usually a template is not a good match for that, because you have only a few characters that you have to append one after the other. So and here is one simplified piece of simplified code snippet from our example that is able to compile an expression, which in this case is a property access, into a C code. So the first line here is says we want to trace the whole expression from our source AST, and we get a composite node as a result. And then we can call these append extension methods here to add content to that composite node. So first we add the type, then the result variable name, an equal sign, receiver variable name, some arrow sign, and then the actual feature name that we want to access. And so all these append statements make sure that we have the correct output code, and the trace method here makes sure that all this collected output code will be mapped to this expression. So, as I said, this is part of our example, so you can have a look at the GitHub repository and check it out and see how that is done exactly. So now let's see this in action. I did not take the time to write a debugger exactly for this example language. So if we could imagine doing that, connecting to the C development tools or something like that. But here, what I want to show here is just the features that Xtext offers out of the box without anything you have to add. For example, you can, when you open a DSL source file in Eclipse, you can right-click at any point and say Open Generated File. In this case, it opens up a dialog because from each source file I generate two output files, a C header file and a C implementation file. If it's only one, then you don't see this dialog. So let's take the implementation file, and as you can see, it selects automatically the region in the output text which is generated by the element that I have selected here in the source, which is in this case the get cache operation. And get cache, as we can see now, is transformed to this code region here, and here the name of the get cache operation is transformed to this part here. And we can also go the other way. So if I can select some region here in the generated file, right-click and say Open Source File, that will lead me to the exact location in the source where that was generated from. So here the access to the bag property is translated to this line of code here. And then there's another very useful feature that is good, especially good for debugging your code generator and the traces. If you open your project in the navigator view, you will see also the hidden files, and this includes the generated trace files that are right next to your generated files in the output folder. These trace files contain all the tracing information in a special format and are interpreted by Xtext. And Xtext also ships with a viewer for these files, which you can use to examine exactly what is the result of your trace information. So here on the top you see a tree structure, which is the nested structure of the traces that you have generated. And below you see a view of the source and target. So on the right is your source DSL, on the left is the target C code. And you see regions that are marked with indices. So like here, the region number 1, or let's say here, the region number 1 is from here to here in the source, and the corresponding target region is here also with the index 1. So here we see that exactly, so the whole operation get cache is translated to this target code region. Or more fine-grained, there is another region with the index 6 here, which is the property access to bag, and this is translated to exactly this line of code as we have seen before. So usually you wouldn't use this for or offer this to your users or to your end users or anything, but it's, as I said, very useful for debugging. Good. As I said, I currently can't offer a debugging demo for this example, but I can do that for another example DSL. And to make things a little bit more interesting, I have not used the Eclipse integration for that, but instead the Xtext Web Integration. As many of you probably know, this new integration has been introduced about 1.5 years ago in Xtext. It allows you to get started very quickly with writing web applications for your DSLs. So as a result, you get a web page which is served by a Jetty server that runs locally here on my machine, and you have a rich text editor. In this case, it's the ACE editor, the same that is also used by GitHub. And here you have content assist, and you have validation. So everything that, well, not everything that you know from Eclipse. So the feature set is a bit less than that, but at least the most important features are there. So this is not new, but what is new now is that let's have a look at this at the source of this web page. Those of you who have been already working with web applications know that most modern browsers offer debugging support for JavaScript. And in this case here, I can my target code for this DSL is actually JavaScript, and I can execute the JavaScript code by clicking this Run button. So, and this displays the value that is behind this output statement here in a message box. So, and now in my developer tools, I can go to the sources, to the index.html, go to the exact piece of code that executes my generated JavaScript code. Then click the Run button. Now, okay, I am now in the breakpoint. Now I will now step into this execute JavaScript method, which points me to the generated code. Step into, and now you see the cool part. Now the development tools of Chrome shows me the source DSL code instead of the generated Java code, and this is because next to the JavaScript code, I have also generated a source map, which is in a standard format that is understood by the modern browsers, and that specifies which is the source that corresponds to the JavaScript code, and which is the mapping between source code regions to target code regions. So here I can actually step through this code, and you even see the intermediate values of the variables. So now we have come to the output statement. If I execute this one, then I get the output here. So, and I can also have a look at how the generated JavaScript code looks like. And here you see there's a comment down here. So this is just a convention. There are other ways to specify which is the source mapping, so you don't have to do this with a comment, but so this is a very easy way to do that. And this comment contains a URL that points to the generated source map. And I can open this one in my browser. And then we see that the source map is actually in a JSON format. So that's nothing that we have invented. It's just a standard that is used by all the modern JavaScript transpilers. So and inside this source map, you see some name of the source file, and you see a mappings section with a lot of characters. These are base 64 encoded source to target mappings in a quite special format that is optimized for a compact and short representation. And then also at the end of this file, you see the actual source code. So so the Chrome debugging tools pick up this JSON file, display the source code, and use these mapping information to step through the source code. Good. Yeah. Then let's finish with this.
Oh, sorry. So thanks, Miro, for the demo. There's one more thing we would like to tell you about what we can do with the tracing stuff. And so far we have seen we can use it for debugging, we can use it for just navigating, but I have another use case. there may be use cases where debugging the debugging the DSL is simply not possible because the generated code runs on some small device or something where you cannot connect somehow to the IDE. So immediately or directly debugging in the DSL editor is not possible for several reasons. And so people go to the generated code, fix their bugs there. And we were repeatedly from time to time asked, how is it is it somehow possible to feedback these changes in the generated target code back into the DSL? And our first message is, so yeah, we strongly encourage that other people. So don't stick to just the changes in the target, but feed them back to the DSL, as otherwise your sources will diverge, and in the target you lose all the benefits from the DSL. So just switching to the target and continue there is not a good idea. Put the stuff back into the changes back into the DSL, and we're currently experimenting with an approach that is also enabled by this tracing information. So what we're doing is, what we're attempting is to compare the source and the target code, and not just doing it by text compare, but doing it smartly. So what happens here, or what I try to illustrate here, is we have on the right the target code that has been modified in this area. And here we have our original source, and what the tool does is compare the target code that would be generated from this source with the actual modified target code, determine the differences, and by means of the tracing information map this back to the DSL and illustrate the diffs this way. So this is something we do not have done yet, but we are kind of curious about, and I guess if it will work, we will maybe tell you next year about this. So stay tuned. That's it so far. Find the example of Miro on GitHub via this link. And if you liked our talk, give us a +1. And if you didn't, let us know, please. Thanks. So the question is, you have several models as an input and one output or so?
Yes, well, it is possible, but that has problems. So the general assumption for this Xtext generating infrastructure that has nothing to do with the tracing, it's more about generating code in general, is that you generate one or more output files for one source file. Whenever you have this n to 1 generating code, it can be a bit difficult, but so yeah, you can solve these difficulties, but in general, if it's possible, I would rather recommend you to not do that, but yeah, maybe we can talk later about that. Yeah?
So the question is, I used the term smart comparison or smart compare, and the question is what it is about. Just to let me go back to the slide. Yeah, I just explained it briefly. Here on the left, we see the DSL, but we do not immediately compare the DSL with the generated code, but we translate the DSL to generated code and compare that one with the modified generated code. So this is the code where users put their fingers in, and behind this representation, behind this DSL source, there's the code that would be generated by our code generator. And there are some differences. And these differences basically are computed by means of textual compare. But then we would have, corresponding to this change, we would have something on this side. And based on our tracing information, we can map this back to the DSL source, to the code region in the DSL specification, in the DSL program. And then we can, or we at least we hope we can make this obvious this way, or emphasize it this way. Yes?
In that example, I guess it would be impossible to convert from type language to return back to the DSL.
Yeah.
That would be impossible.
So it would be, in general, it is impossible to have an automatic merge to left button or so. That's true, because we would need to have a parser for the target code and have the code generator backwards basically. Yeah, but we can at least indicate it, and for some things, imagine that this is not code, but say kind of structured data in comma-separated fashion or similar things, and we at least hope that in that case it can be partly possible.
Could that possibly work with text-based languages? I know this is you said the text-based why not works already.
Maybe, yeah, at least for the expression part, because if you do not have, for simple binary operators, I could imagine that it is possible, because they are.
You have to code that convert Java, extend, and then you use whatever. Maybe.
Yeah, maybe. So partly I could imagine if you have some fancy switch statement with type checks and expressions and so on, and then I could imagine it could get a bit difficult. At least you could more fine-grained changes make here that are not directly mappable to these other expressions. Could imagine. This is more a semi-automatic means.